Welcome to lecture number 19 on measure and integration. In the previous lecture, we had started looking at the properties of integral for non-negative measurable functions. We had looked at the linearity property of the integral for non-negative measurable functions, and then we said we will start looking at the limiting properties of functions which are non-negative measurable and integrals of them. So, today we will prove some important theorems. We will start with proving what is called monotone convergence theorem, and then we will prove Fatou's lemma, and then go over to define integral for general functions. So, let us look at what is called monotone convergence theorem. Monotone convergence theorem says that let f n be a sequence of functions in class L plus. That means, f n is a sequence of non-negative measurable functions increasing to a function f of x at every point. That means, f of x for every x in x is limit n going to infinity of f n of x. So, we are given a sequence f n of non-negative measurable functions which is increasing and the limit is f of x. Then the claim is the function f belongs to L plus. This we have already observed, and the additional property is that the integral of the limit f d mu is same as limit of the integrals of f n d mu. That means, whenever a sequence f n of non-negative measurable functions increases to f, then integral of the limit is equal to limit of the integrals. So, this is the first important theorem about convergence of sequences of non-negative measurable functions and their integrals. So, let us prove this property. So, we are given f n is a sequence, each f n belongs to L plus, is a non-negative measurable function for every n bigger than or equal to 1. So, that means, that implies there exists a sequence, we will denote it by S n j of functions n bigger than or equal to 1, such that S n j are non-negative measurable simple functions for every n and for every j, and S n j increases to f of. So, let us fix the notation which one we are going to vary. So, let us say that the upper one will be fixed. So, this is going to f n as j goes to infinity. So, for every n fixed, S n j is a sequence of non-negative simple measurable functions increasing to f n's, and f n's they increase to f. So, we want to show, we have already shown, but we will show it again, that this implies f belongs to L plus is a non-negative measurable function, and integral f d mu is equal to limit n going to infinity integral f n d mu. So, to prove this, we are going to use this sequence S n's and construct a new sequence of non-negative simple measurable functions out of it. So, what we will do is the following. So, let us write that for n is equal to 1, okay, that S 1 1, S 1 2, S 1 j, S 1 say j, this converges to f 1. So, the upper index is going to give you. So, S 2 1, S 2 2, S 2 j, this increases to f 2, and in general we will have S n 1, S n 2, S n j will increase to f n, okay, and so on, and this increases to f. So, let us observe that as we go from left to right, this is increasing. So, everywhere left to right it is increasing, and down to up that also is increasing. So, every sequence, if you look at the, so this is a array of non-negative simple measurable functions. Each row is increasing to the function on the right side, and this is increasing upwards. So, let us out of this I am going to define. So, let us look at the function. So, let me define from this a function. So, let us define g n to be the function which is maximum of s and j between 1 and n. So, look at in a sense what I am doing is, in this picture look at the one. So, let us say here is S 1 n, and here is S 2 n, and here is S n n. So, I look at this column. So, S 1 we are looking at the column S n 1 S n. So, let us look at this column. So, and call that maximum of this to be g n. Okay. So, what is g n? So, g n is the, so let me write again. So, g n is the maximum. So, define g n equal to maximum of S j n j 1 to n. So, so let us observe that each g n is a maximum of non-negative simple measurable functions. So, each g n is a non-negative simple measurable function for every n, and g n is increasing because at the next stage n plus 1. So, all this is going to be bigger the next stage. If we look at g n plus 1, so that is going to be S 1 n plus 1, S 2 n plus 1, and so on, S n plus 1 n plus 1 n, and S n plus 1 n. So, all this one is going to be bigger than everything on the left hand side, okay. And these are we are looking at the maximum. So, in the maximum of this is going to be bigger than or equal to maximum of this, because at each the right hand side function is bigger than the left hand side function. So, this is going to give us that is g n is a increasing sequence of functions. So, let us write, let g be equal to limit n going to infinity of g n. So, g is, so all these g n's are increasing, and they are going to increase to some function g. So, what we are going to show is g is equal to f. Okay. So, that is what we are going to check. So, let g be equal to, so then clearly by definition g is a non-negative simple measurable function, because it is a limit of a increasing sequence of non-negative simple measurable functions. So, g belongs to L plus. Also, let us observe also each g n is less than or equal to f n. Each g n is less than or equal to f n for every n, right. So, that is because, see, g n is the maximum of this. So, and the maximum of this, each one of them is less than f 1, is less than f 2, is less than f n. So, the maximum of these g n's is going to be less than or equal to this f n for every n, and f n is increasing to f. So, that will imply that, so g n is less than or equal to f n for every f, and f n is less than or equal to f. So, implies that g n is less than or equal to f n and is less than or equal to f for every n. So, hence and g n is increasing to g. So, that implies g is less than or equal to f. So, that is one observation, that the function g is less than or equal to f, and we claim that the other way around is also true. So, claim is that f is also less than or equal to g. So, let us note that for every j between 1 and n, if I look at S j n, g n is the maximum of this. So, this is less than or equal to g n for every n. So, this is less than or equal to g n for every n, and j between less than this. So, if we fix and g n is less than or equal to, and this is less than or equal to g. So, S j n is less than or equal to g n is less than or equal to g for every j between 1 and n, and for every n. So, let us now fix j and let n go to infinity. So, as n goes to infinity, what happens? So, this converges to f n. So, note that as n goes to infinity, S j n goes to f j. So, from this and these two observations, S n j is less than or equal to g for every. So, if we fix j and let n go to infinity, then n is going to cross over j, and S n j n as n goes to infinity converges to f of j. So, this implies f of j is less than or equal to g for every j. So, we get, so implies that f j is less than or equal to g for every j, and f j's are increasing. So, this implies that f is also less than or equal to g. So, we have already shown g is less than or equal to f, and now we are saying f is less than or equal to g. So, this implies that f is equal to g. So, hence, one observation from here is hence that g belongs to L plus. So, f belongs to L plus. Okay. So, we have once again proved that if f n's are increasing to a function f and f n's are non-negative measurable, then f is also non-negative measurable. And now, note that integral of f d mu is same as integral of g d mu, because f is equal to g, and this is equal to limit n going to infinity of integral g n d mu, because g n's are non-negative simple measurable increasing to g. So, by definition this is so, but each g n is less than or equal to f, if you recall. So, each g n is less than or equal to f. So, integral of g n will be less than or equal to integral of f. So, limit of integrals of f n's will be less than or equal to integral f. So, this is less than or equal to integral f d mu. Okay. Or we can even introduce in between. So, g n is less than or equal to f n. So, it is less than or equal to limit n going to infinity integral f n d mu, which is less than or equal to integral f d mu. So, what does this imply? Integral f d mu is less than or equal to limit f n integral of f n d mu, and that is less than or equal to f d mu. So, that implies that integral of f d mu is equal to limit n going to infinity integral f n d mu. So, that proves the theorem completely, namely integral of f d mu is equal to limit n going to infinity integral of f n d mu. So, this is a construction which is quite useful in. So, this is the kind of analysis one has to carry out. So, let us go through the proof again, so that we understand what we are doing. Each f j or f n is a measurable function. So, I can look at a sequence S 1 1, S 1 2, S 1 j, S 1 n, which is going to increase to f 1. Similarly, the upper fix is fixed at 2. So, S21, S22, S2j, S2n, that increases to F2 and so on. So, each row is increasing to the function on the right side, and the functions F1, F2, Fn's are increasing to the function f. So, what we do? We look at the maximum of this column. So, what is this column? This column is the maximum of the functions S1n, S2n and Snn. So, call this as Gn. So, this function is called Gn. So, the observation is each Gn is a maximum of non-negative simple measurable function. So, it is non-negative simple measurable. Each Gn is less than or equal to Fn, because we are going up to this corner only. Okay. So, each Gn is less than or equal to, because S1n is less than F1, S2n is less than F2, F1 is less than F2 and so on. So, this says Gn will be less than or equal to Fn, and each Fn is less than or equal to F. So, each Gn is less than or equal to Fn is less than F. So, if we write the limit of Gn to be, so we write the limit of this to be equal to G, then G is less than or equal to F by this simple construction. Also, for any fixed j, let us look at S and j. So, let us look at S and j, where j is fixed and n is going to vary. So, as n varies, what happens to these functions? So, for every fixed j, this sequence of functions is going to be S and j is less than or equal to G n, okay, and G n is less than or equal to f. So, we let G is less than or equal to f. So, S and j is less than or equal to G n for j between 1 and n. So, that will give us that f is also less than or equal to G. So, that will prove the theorem that limit of increasing sequence of non-negative measurable functions, if Fn is a sequence of non-negative measurable functions increasing to f, then integral of f d mu is equal to limit of n going to infinity integral Fn d mu. So, this is called monotone convergence theorem. Monotone, because we are looking at monotonically increasing sequences Fn, and convergence, because we are looking at the convergence of the integrals of integral Fn d mu. So, this proves monotone convergence theorem. And let us remark, we have proved the theorem monotone convergence theorem for when Fn is a increasing sequence. So, naturally the question arises, will the similar result hold if I have a decreasing sequence Fn of non-negative measurable functions? That result unfortunately is not true. So, here is an example which says that if Fn is a sequence of functions which are non-negative measurable and they decrease to a function f, then integral of f need not be equal to integral of Fn d mu. And the example is on the Lebesgue measurable space. So, look at x to be the real line, the sigma algebra to be the sigma algebra of Lebesgue measurable sets, and mu to be the Lebesgue measure. Now, look at the function Fn, which is the indicator function of the interval n to infinity. So, the claim is, so this is actually a non-negative simple measurable function each Fn, and Fn is decreasing and decreasing to the identity function identically equal to 0. That is quite obvious to see. So, what is Fn? So, we are looking at, so here is n, and we are looking at the interval n to infinity. So, we are looking at this interval, okay, and we are looking at the indicator function of n to infinity. So, the function is 0 and it is 1 here. So, the function is, this height is 1. So, this is the function Fn. It is 0 here up to here, and then it starts and goes. So, that is the function Fn. So, if we take n plus 1, so this is n plus 1. So, n plus 1 will be 0 here, but Fn is equal to 1 here. So, clearly Fn of x is bigger than or equal to Fn plus 1 of x for every x. So, Fn is a sequence in L plus and f n is decreasing, and the claim is f n decreases to f of x, which is identically equal to 0 for every x, and that because if I take any point x on the real line, then I can find some integer n, say n naught, which is on the right side of it. Then so for every x belonging to real line fixed, I can find a point n naught, a positive integer n naught. Of course, it will depend on x such that n naught of x is bigger than x. So, that will imply that the indicator function of n naught to infinity or n naught to infinity, let us even n to infinity at x is going to be equal to 0 for every n bigger than or equal to n naught, and that is my f n of x. So, f n of x is equal to 0 for every n bigger than n. So, that means f n of x converges to f of x, which is equal to 0. So, f n is a sequence of non-negative measurable functions, which is decreasing to f identically 0. But if we look at the integral of each f n, so what is the integral of each f n? So, integral of f n d lambda. So, this is integral of the indicator function n to infinity d lambda. So, that is equal to lambda of n to plus infinity, and that is equal to plus infinity for every n. So, integral of f n is equal to plus infinity for every n, and integral of f d lambda is equal to f is 0. So, it is 0. So, this implies that integral f n d lambda does not converge to integral f d lambda whenever f n is a decreasing sequence of function, non-negative, simple, non-negative, even simple functions we have given example here. So, for decreasing sequences this result does not hold. So, that gives importance to the monotone convergence theorem. That means, whenever a sequence f n of non-negative measurable functions is increasing, then integral f is equal to limit integral f n d mu. For decreasing, this need not hold. So, this is what we have shown just now by an example. So, however, one can prove not an equality, but some kind of an inequality for a sequence of non-negative measurable functions, and that is also an important result. So, let us prove the result, which is called Fatou's lemma. It says, let f n be a sequence of non-negative measurable functions, then the integral of limit inferior of f n d mu is less than or equal to limit inferior of the integrals f n d mu. So, this is only an inequality and it need not be an equality. So, what we are saying is, if f n is a sequence of non-negative measurable functions, then it is always true that the integral of the limit inferior of f n's is less than or equal to limit inferior of the integrals. So, let us give a proof of this theorem. So, to prove this theorem, so let us just first recall what is. So, f n is a sequence of non-negative measurable functions. So, each f n is a non-negative measurable function, and we want to look at limit inferior of f n as n goes to infinity. This is a function. So, let us observe how this function is defined. Limit inferior of f n at a point x is defined as, you take the infimum from some stage onwards. So, m bigger than or equal to n of f n of x. So, look at the numbers f n of x, f m of x for m bigger than or equal to n. So, I am looking at the tail of the sequence f n of x from m onwards. So, this number infimum will depend on m. So, let me take the supremum of this overall m. So, first take the infimum from some stage onwards and then take the supremum of these infimums. So, let us observe that this infimum, let us put a bracket here. So, observe. So, let me call it as phi m to be the infimum from the stage n onwards. So, infimum of m bigger than or equal to n of f n of x, phi n of x to be defined as the infimum from the stage n onwards of f m of x. So, then because it is the infimum of a sequence of functions which are non-negative measurable. So, clearly, so note, so observation is that each phi n is also a non-negative measurable function. So, it is a non-negative measurable function, that is one. And secondly, we are taking the infimum from some stage n onwards. So, if we increase, so the claim is this phi n is increasing. This is an increasing sequence, because phi, so phi n from the infimum from the stage n onwards is going to be less than or equal to the infimum from the stage n plus 1 onwards, because we will have more numbers for which you are taking infimum. So, infimum can when you take infimum over more numbers, then infimum can decrease. So, infimum from the stage n onwards and the infimum from the stage n plus 1 onwards. So, that says that the infimum from the stage n plus 1 onwards will be bigger than or equal to the infimum. So, increasing, that is phi n plus 1 is bigger than or equal to phi n of x for every n. So, it is an increasing sequence of non-negative measurable functions, and its limit is nothing but the limit inferior. So, it is increasing, and so it is increasing, and limit n going to infinity of phi n is equal to limit inferior of f n going to infinity. So, the stage is set perfect for an application of monotone convergence theorem. Phi n is a sequence of non-negative measurable functions, phi n's are increasing. So, by monotone convergence theorem, so we can apply implies by monotone convergence theorem, by monotone convergence theorem, that integral of limit n going to infinity of phi n d mu is equal to limit integral phi n d mu n going to infinity. So, this is nothing but, so this side is nothing, left hand side is nothing but integral of limit inferior n going to infinity of f n d mu. So, that is equal to limit of integral phi n's. Now, let us look at what is phi n. Phi n is the infimum from the stage n onwards. So, each phi n is less than or equal to f n. So, that is the observation from here. By the definition of phi n, we have that each phi n is less than or equal to f n. So, integral of phi n will be less than or equal to integral of f n. So, it will be less than or equal to limit inferior of n going to infinity. So, what we are observing here is, because each phi n is less than or equal to f n. So, this implies, so this is what we are using here, that each phi n is less than or equal to f n, then the n limit and integrals of phi n's are increasing. So, it limit exists. So, limit n going to infinity integral phi n d mu is less than or equal to, however, integral of phi n f n's may not exist. So, we can say that it will be less than or equal to limit inferior of integral f n's d mu. So, this is what is being used in this conclusion, and that proves the theorem what is called the Fatou's lemma.